Welcome back. We got a couple more videos to talk through, a couple more concepts to work with together, so let's get to it. So far in this section, we've looked at how to use logarithms to solve exponential equations. In this video, we're going to look at how to use exponentials to solve logarithmic equations. So read over this situation with me here. Suppose we're running a company and it sells products, and the number of products we sell depends on how much money we spend advertising. Makes sense? More money we spend, the more people buy our stuff. However, it's not one to one, right? If I spend $1 more, it's not like I'm going to get one more sale, right? The more I spend, the more people buy, sure, but the fewer more people buy. I'm subject to something that's called diminishing returns. So suppose for me that this is the model that we use to determine the relationship between how much we spend in advertising, that's A, and how much we actually sell, that's N. So first things first, just play with this a little bit. How many units would we expect to sell if we spend just $1 in advertising? And how much if we spend 1,000 or 1,000,000? And we'll answer that first, then we'll get to this harder question where we'll work backwards to determine how much we would need to spend in order to sell 20,000 units. Definitely worth knowing. So first things, we're just going to substitute some values, right? We've got N, which is what we want, and A, which is what we've spent. And A will go into our model 3 different times. For A of 1, I actually don't need a calculator here, because the natural log of 1, that is asking E raised to what power gives me 1? Well, anything to the power of 0 is 1. Well, except for, I guess, 0 to the power of 0. Anything else to the power of 0 is 1. So the natural log of 1 is 0. That goes away. And I am left with 4,500 units sold if I spend $1. If I spend $1,000, 1,000 goes in for A. I will need a little bit of help running that computation, right? So 1,000 times natural log is about 6.9, etc. I then multiply that by 400, because that's what my equation dictates. Add 4,500 to that, and I get 7,263.10211. And if you're like some of my students, you'll stop there. And if I'm like me, which I am, I will get mad because I asked you how many units am I selling, right? I want to know how many units am I selling? Like how many customers am I going to have? You're going to tell me how many customers I'm going to have, not to the nearest decimal, not to the nearest tenth or the nearest hundredth. You're going to round down. You're going to give me 7,263 units being sold here, because that makes sense physically. Next up, we're going to start to see diminishing returns here pretty quick. If I spend $1 million, I'm only going to sell about 3,000 more units. So we hit diminishing returns fairly quickly here. Definitely, well, probably worth spending $1,000, almost definitely not worth spending $1 million. Again, based on our model. And if we want to work backwards, let's build up for that first. Right, remember what I said earlier, that if you take the logarithm of both sides of an equation, you can undo an exponential. The logarithm of 10 to the 5th is 5. Natural log of e to the 7th, that's asking e raised to what power is e to the 7th? That's just 7. Log base 12 of 12 to the x, that's just x. Well, it also works in reverse. I can also do an exponential of a logarithm to get what's inside the logarithm. So not only is the log of 10 to the 5th 5, 10 to the power of log 5 is also 5. E to the power of natural log of 7 is 7. And 12 to the power of log 12 of x is x. And that is how we solve logarithmic equations. So let's go back to trying to sell 20,000 units. In goes 20,000. We will solve for the natural log and then do an exponential. So first I'll subtract to get 15,500 is equal to 400 natural log of A. Solve for natural log by dividing by 400. And now I've got about 38.75 is equal to natural log of A. So I will raise both sides to be a power of A, and we'll find that A, the amount of money we need to spend, is about $67 quadrillion. That's a problem.